We would like to extend our warm welcome to all participants of the second day of short course Nature X ScienceTech Innovation, Co-Creating Sustainable Agro-Food Industry and Climate Solution for Resilient Planet, which is organized by the Faculty of Agricultural Technology, UGM. Just in case you're forgetting, let me introduce myself again. My name is Indah Suma Putri, and you can call me Puput, and I will be the MC for this morning session. Today, we have a series of intellectually engaging and insightful sessions delivered by distinguished speakers from various institutions, both on-site and online. We will begin with Professor Cheng-I from National Taiwan University, Taiwan, who will be joining us virtually via Zoom. Next, we will hear from Professor Kunchoro Hartowidodo from Universitas Gadjah Mada, Indonesia, who will be joining us here in person. Following that, Professor Particolai from KU Leuven, Belgium, will continue the session on site. Then Dr. Arimadia Setiawati from Universitas Gadjah Mada, Indonesia, will join us on site to share her insight. Each speaker will contribute their expertise and perspective to enrich today's discussions, and every session will be guided by a moderator familiar with the respective topics. Okay, moving to the first session, the topic is about climate resilience through microclimate management from field condition to practical interventions by Professor Cheng-I from National Taiwan University. They're joining us virtually via Zoom, and this session will be led by our moderator, Mr. Nafis Rizkullah Azim STPMS. And let me introduce his CV for you all. Mr. Nafis Rizkullah Azimi STPMS is a lecturer at the Department of Agro-Industrial Technology, Universitas Gadjah Mada, with a strong academic background in biodegradable packaging, biomaterial and packaging technology, and he earned his bachelor from UGM and master degree from Kasetsart University, Thailand. He has led and contributed to various research projects and publications related to biodegradable packaging and technology, and also biomaterial. Without further ado, please welcome our moderator in the session, Mr. Nafis Rizkullah Azimi, STPMS. The time is yours.
Okay, thank you very much for your introduction. So good morning, everyone. You already wake up, right? It's quite a morning in today. So I hope that you can follow our session. So yes, my name is Nafis, and today I will be your moderator for the first session. So before we go, I think our speaker was here, Professor Cheng. Can you hear me clearly, right?
Yes.
Okay, thank you. And before I go, I will introduce our speaker first. So, our speaker is Professor Cheng-I from National Taiwan University, and he was finished his study in doctoral study in Duke University School of Environment in Durham, USA. Actually, he from National Taiwan University, and his research area is about environment, greenhouse gas emission, micrometeorology, and sustainability. And he have some publication they have one in 2026 about the water demand prediction approach using adjustable self-feedback gain element neutral network coupled with the enhancement spiral search algorithm. And another is about the evaluation of the water efficiency and yield on the shallot cultivation under conventional irrigation and sensor-based drip irrigation. And also he has some award is Academic Award of Agricultural Engineering by Taiwan Agricultural Engineering Society. And the second one is Senior Excellent Teacher Award by School of Bioresource and Agriculture National Taiwan University. So this opportunity is very good for us, especially for myself. We can learn the things that maybe is very common, very new, and we can we can learn together. And His presentation is about the climate resilience through microclimate management from field condition to practical intervention. And I will not waste the time, so I think now the time is yours, Professor Cheng.
Yes, thank you very much. So should I share my slide from my end?
Yes, right.
Okay. Okay. I think I need the right to share. So now, are you able to see the slide?
Yes, it's very clearly, Professor.
Okay. Very good.
Yes.
So are you able to see the title of my slide? The title slide?
Yes, we are able to see it.
Okay. Thank you very much for inviting me to give this lecture. Today, I will talk about climate resilience through microclimate management, from field conditions to practical interventions. First of all, I will talk about carbon farming, the so-called 4 per thousand initiative. Then I will introduce the micrometeorology technique, the so-called eddy covariance method. This method is commonly used for quantifying the carbon emission and uptake from ecosystems. Then at the end, I will talk about microclimate practical interventions. Several methods will be discussed in this part, including frost fan, wind tower, water spray system, green roof, cool roof, and solar panel. So for the nature-based solutions with the capacity of ecosystems to uptake or emission carbon dioxide. Here are some results recently presented by Professor Timo Vasela from University of Helsinki. Their newest results show that for pine forest, uh, the capacity of uptaking carbon dioxide from the atmosphere is minus 300 gram carbon per square meter per year. Minus sign means uptaking carbon dioxide from the atmosphere. The plus sign means emission carbon dioxide to the atmosphere. So for pine forest, it's about minus 300 gram carbon per square meter per year. But for a peatland, it's only minus 50. So the capacity is very different. So if we are relying nature-based solutions to combat climate change, then we have several choices, and maybe forest is a better choice. And for urban ecosystem, we can see that it's producing carbon dioxide into the atmosphere. And for road sector, the amount is very big. It's plus 3,000 gram carbon per square meter per year. So now for carbon farming is a path to combat climate change through agricultural sector. Carbon farming is a set of agricultural methods that aim to store carbon in the soil, crop roots, wood, and leaves. The technical term for this is carbon sequestration. The overall goal of carbon farming is to create a net loss of carbon from the atmosphere. So this is done by increasing the rate at which carbon is sequestered into soil and plant material. One option is to increase the soil's organic matter content. For example, for this cornfield, actually this cornfield belongs to my family. After harvest, a tiller was used to grind the remaining core stalks, roots, and leaves into the soil and increase the soil organic carbon. So the efficiency of carbon farming depends on the photosynthetic rate of your crops. So carbon farming is one component of climate smart agriculture. It is also one way to remove carbon dioxide from the atmosphere. And this is the origin of the idea of 4 per thousand initiative. So now let's talk about 4 per thousand initiative. This is one of the initiatives in Paris Agreement 2015. So if the level of carbon stored in the top 30 to 40 centimeters of soil is increased by 0.4% or 4 per thousand per year, the annual increase of carbon dioxide in the atmosphere would be significantly reduced. So the Vision 4 per thousand initiative is worldwide healthy and carbon-rich soils to combat climate change and end hunger, because this is relying on your crop planting, and so can end two things together: climate change and hunger. However, there are some problems in carbon farming. When organic matter in the soil is exposed to the air, it is easily oxidized and carbon dioxide is released to the atmosphere again, and this is the so-called soil respiration, especially when soil organic carbon is increased. So then we need to measure how much carbon is released into the atmosphere from the soil, and how much carbon is uptaken by the crops from the atmosphere into the soil. So measuring and verifying carbon storage for generating carbon credits are needed. And the actors like FARA and the gold standard play a crucial role in the voluntary carbon market. Anyway, first of all, we need to quantify the carbon credit from carbon farming, and this is to measure the carbon dioxide uptaking rate by the ecosystem or by your crop farms. So measuring soil respiration on agricultural land or carbon farming enhances carbon sequestration in the soil. So these are the methods that we are using to quantify carbon farming and the soil respiration. And here you can see these are based on chamber method. But the problem with chamber method is that the sample area is limited. And and nowadays, the most accurate and reliable method is the so-called eddy covariance method. Then we will introduce this eddy covariance method in the next section. So these are the experiments that we are doing with University of Helsinki in Finland above a peatland. Now, let's move to the second part of this talk, micrometrology technique for measuring CO2 emission and uptake, the so-called eddy covariance method. The eddy covariance method system is also a micrometrology station and can be used for precision agriculture management, because this is also a local meteorology station and it can provide local climate data for your agricultural need and for more precisely plant your crops. Now, so this is the idea of the so-called smart agriculture. And with this smart agriculture or precision agriculture, we need micrometeorology monitoring system, and the eddy covariance system is part of these systems. The soil consists of two parts. The first part is the sonic anemometer to measure wind speed. And the second part is an open path or closed path gas analyzer to measure your greenhouse gases like carbon dioxide, methane, and nitrous oxide, N2O. And here I will use carbon dioxide as an example. Before we go to the eddy covariance system, we have to introduce the background of this eddy covariance system. And first of all, the eddy covariance system, to quantify the capacity of uptaking or releasing carbon dioxide into the atmosphere from an ecosystem, is by a parameter called flux. So flux is nothing but quantifying how many grams of carbon dioxide is released or uptaken from the atmosphere by per square meter per second. So it can be quantified by how many moles of carbon dioxide instead of how many grams per square meter per second. And the flux by these units is nothing but velocity times concentration. So for example, you see velocity is in unit of meter per second. Concentration is in gram of carbon dioxide, of gram of methane or nitrous oxide of the greenhouse gases that you are interested in per cubic meter. And then you have, and then meter per second times gram per cubic meter ends up with gram per square meter per second. This is why our eddy covariance system consists of two parts: the sonic anemometer to measure the velocity, and a gas analyzer to measure the concentration. So by measuring this quantity, the flux, we can quantify the capacity of an ecosystem to uptaking carbon dioxide per square meter per second from the atmosphere, or release carbon dioxide into the atmosphere per square meter per second. And this method is based on conservation of scalar mass, or the so-called advection diffusion equation. So the basic idea is that in a control volume, we calculate the flux into the control volume minus the flux out of the control volume. Then it equals to the storage of the greenhouse gases in the control volume. So for the advection flux, and the flux can be divided into two parts: the advection flux plus diffusion flux. Advection flux is a result from the wind speed. A diffusion flux is a result from molecular diffusion. So advection flux can be represented by the following equations, that here U, V, W are the wind velocities along the x-axis, y-axis, and z-axis. So for example, W is actually the vertical wind velocity. U is the horizontal wind velocity in the x-axis. V is also the horizontal velocity, wind velocity in the y-axis. So the advection flux can be represented by velocity times the concentrating gradient, partial C over partial X, and partial C over partial Y, and partial C over partial Z. So the second term is the advection flux. Then the diffusion flux is calculated by the so-called Fick's law. Here, diffusion by Fick's law. Here, Fick's law describes the flux quantity by molecular diffusivity. And nu d is the molecular diffusivity. It has the unit meter per second times meter, and then times the velocity gradient in the vertical direction. Here, actually, we have three directions in x direction, y direction, and z direction. Here, I only show you the Fick's law for the vertical direction only. Now, this is the diffusion flux from molecular diffusion from a higher concentration to a lower concentration. Then these two parts equals to the change of scalar mass in the control volume. So the change of scalar mass in the control volume can be represented by partial C over partial T. Here again, C is the concentration of greenhouse gases in the control volume, and T is time. And then also in this control volume, there may be a source, which is our forest or our crop from our farmland. And this is represented by the parameter S. So the source term has the unit of uh, grant per cubic meter per second. Now we have to apply the Reynolds decomposition and averaging into this diffraction diffusion equation. So the Reynolds decomposition decomposes the instantaneous concentration into mean concentration plus fluctuation. So C means the instantaneous concentration that you measured by your gas analyzer at the moment. And the C bar, the over bar denotes averaging. So C bar equals sigma Ci, I equals 1 to n, and divided by n. N is the total number of your sampling. So normally in this eddy current system, we have a sampling frequency of 10 Hertz. And the sampling period is 30 minutes. So the total sampling data size is 10 Hertz times 60 seconds, time per second. So the total is 18,000 per half hour. And then instantaneous is decomposed to the mean within these 30 minutes, plus the fluctuation, here denoted by C prime. So if we have this signal, here, this part is the instantaneous concentration C, divided into two parts, the mean part, C bar, and the fluctuation C prime. So C prime can be positive or negative. In here, it's negative because it's under the mean value. So C here is the instantaneous concentration C, and this is the mean, and here is the C prime. So after we replace here the instantaneous concentration C with C bar plus C prime and take the averaging, we can get the mean mass conservation equation for a diffraction diffusion equation. So instead of partial C over partial T, then here we get partial C bar over partial T. Again, C bar is the mean concentration for the 30 minutes sampling period. So we have partial C bar over partial T representing the storage term, and the U bar times partial C bar over partial X plus V bar times partial C bar over partial Y plus W bar times partial C bar over partial Z as the diffraction flux, a diffraction term for this diffraction diffusion. And then we will have an extra term. This term is the so-called turbulent flux divergence term because it has the turbulent flux U prime C prime bar times and V prime C prime bar and the W prime C prime bar, and take the divergence of these three fluxes, and then equals to the source term. And by assuming steady state and horizontal homogeneity and neglect subsidence, which means W bar equals to 0. So if W bar equals to 0, this term is finished. U bar in the partial C bar over partial X based on the horizontal homogeneity assumption, partial C bar over partial X is 0, 2. And the partial C bar over partial Y is 0, 2. So these two terms are 0. And also here, partial u prime c prime bar over partial x is 0, 2, and the partial v prime c prime bar over partial y is 0, 2. And we also assume steady state, so it means partial c bar over partial t is 0. So then we end up with these two terms only. Partial w prime c prime bar over partial g equals to the source term. And then we take integral for both sides from 0 to h. Here h is your canopy height because your forest has some height, normally around 10 meters tall, or sometimes it's even taller, be up to 30 meters tall, 60 meters tall, depends on your forest. And so we have to do the integration from 0 to h to quantify all the sources, all the sources from this forest, from the ground to the canopy top. So by taking the integration for both sides, we end up with noting that w prime c prime bar at the canopy top h equals to the integral of the source term plus w prime c prime bar at the ground. So these two terms on the right-hand side denotes the carbon dioxide releasing from the ecosystem or uptaking by the ecosystem of your forest or grassland or peatland. So this is the so-called net ecosystem exchange, and this is what we want to know. However, to measure these two terms are difficult. And instead of measuring these two terms, we are measuring w prime c prime bar at the canopy top. And the w prime c prime bar is the so-called turbulent flux. And this equals to the surface source, which is the sum of these two terms. So, and the w prime c prime bar, if you noticed, this equals to the covariance of w and c. So this is why the name of AD covariance, because prime denotes turbulent part or AD fluctuations. And the w prime c prime bar is the covariance of w and c. So this is why this method is called AD covariance method. So now we notice that our goal is to measure the covariance between the vertical velocity W and your greenhouse gas concentration, for example, carbon dioxide concentration at the canopy top, and then calculate their covariance. Then you will get the net ecosystem exchange for the whole ecosystems. But however, this method relies on very high frequency measurement. So we need to measure three-dimensional sonic anemometer. We need a three-dimensional sonic anemometer to measure three-dimensional wind velocities. And this sonic anemometer can also tell you the air temperature. So for a three-dimensional sonic anemometer, we can measure UVW, the three-dimensional wind velocities and the temperature. And a gas analyzer for water vapor, carbon dioxide, and other greenhouse gases, for example, methane or nitrous oxide. And this can be open path or closed path. However, in this lecture, I will talk about open path gas analyzer only. So the major wind velocity and the scalar concentration simultaneously, we can calculate the covariance between W and C. And we need high frequency sampling, at least 10 Hz. And the sampling period or averaging period normally is 30 minutes. Now let's take a look of how the signals look like. For an example, the wind speed U in the X direction, you can see this is the wind direction, wind speed sampled at 10 Hz. And this is the wind speed V in the Y direction. You can you can notice that the change of these wind speeds are very frequently and in a high magnitude. And this is the temporal variation of the vertical wind speed. Because the mean vertical wind speed is very small, very close to zero. So you can see that this vertical wind speed is fluctuating around zero. And this is the temporal variation for temperature. And here you can notice that there are some abrupt temperature exchanges, and this denotes the eddies from the atmosphere. And here is the CO2 concentration measured by your gas analyzer. Here you can notice that CO2 concentration has a baseline. This is because we have a background CO2 concentration in the atmosphere. And then if your measurement is close to a forest, the forest can uptake CO2 concentration. So sometimes the CO2 concentration is lower, and sometimes for respiration, the CO2 concentration is higher. And this is the result from our eddy covariance system. And the upper panel is the sensible heat flux measured. And you can notice this is a 2-day diurnal cycle for the ecosystem. And during midday, the sensible heat flux is large. You can see this. And then the second panel is the water vapor flux. It denotes evapotranspiration from this ecosystem. And why we are measuring evapotranspiration rate, it is because when the crops or the forest ecosystems are doing their photosynthesis reactions, the photosynthesis reactions uptaking carbon dioxide from the atmosphere, but at the same time it releases water into the atmosphere. So that's why we are measuring water vapor flux also at the same time. And as you can see, water vapor flux is strong in the midday, but very small in the during the nighttime because there's no photosynthesis and there's no evapotranspiration from the surface. And the finally, the carbon dioxide flux. And again, the minus sign means that carbon dioxide is absorbed or uptaken by the ecosystem. And the positive sign denotes that carbon dioxide is released into the atmosphere. So again, in the midday, the carbon dioxide flux is the strongest because the photosynthesis rate is the strongest during midday. Now, let me show you some flux measurement site in Taiwan. So this is a cryptomeria forest in the National Taiwan University experimental forest. And in this experimental forest, we have a flux tower, which is very tall, it's about 40 meters. And on this flux tower, we have two eddy covariance systems here. And we install these two eddy covariance systems at two heights, 32 meter and 40 meter, to measure the carbon dioxide flux from this cryptomeria forest. And the canopy height is 28 meter. Another site is a rice paddy. This rice paddy site is in the northeastern part of Taiwan. It's called Yilan. And this experiment was done by cooperation with the local farmer. So we set up this eddy covariance system above a rice paddy, and this is of course this is after harvest of the rice paddy. So this is during farrow season, and this is during the crop season. You can see this paddy rice was just planted maybe just few weeks ago. So these are the different period during this rice growing season. And so this is the farrow season when the surface is saturated or flooded with water. And this is the farrow season when the surface is drained out. And this is during the growing season. And then the result. For our results from this rice paddy field, well, in this figure, the x-axis is net radiation. So it's the radiation, the available energy from the atmosphere and the sun. And the y-axis is the CO2 flux in units of micromole per square meter per second. And you can see that the CO2 flux is a function of net radiation. And if you have a higher net radiation, you have a higher capacity of uptaking carbon dioxide from the atmosphere. However, you can see here, if the net radiation is greater than about 400 watt, when the CO2 flux is not changing that much. This is because when the net radiation is too strong, then your crop or your forest leaves, they may close their stomata to prevent prevent water leaving the plants. So that's why the photosynthesis rate is not increased when the net radiation is larger than a certain value. And for these two figures, let's look at the upper figure, the left-hand side upper figure first. Again, the x-axis is the net radiation. Y-axis is the CO2 flux. You can see there's no change. And this is because this is during the farrow season, and the surface has no crops or any other weeds. It's flooded with water, so there's no CO2 releasing and no CO2 uptaking. And for this panel, you can see some CO2 uptaking from the atmosphere and some CO2 releasing into the atmosphere by respiration. This is during the farrow season, where the dry land has some grass on it. Now let's take a look about the diurnal variations of sensible heat. Latent heat. Latent heat is described by the red line, and then and the CO2 fluxes. Let's take a look on the left-hand side first, the upper panel. The x-axis is the Julian day. It describes the diurnal cycle of these fluxes. And the blue line is the net radiation. You can see during the midday, the net radiation is the highest. And then with this higher net radiation, we have a higher water vapor flux or latent heat, which is LE. And this is denoted by the red lines. And the green line is the sensible heat flux. Here notice that in this rice paddy, because most of the energy from the net radiation is used for evapotranspiration, so only a small amount of energy is distributed to the sensible heat flux. So here you can see the sensible heat flux is quite small. Now let's move to carbon dioxide. And again, you can see that during midday, the carbon dioxide reaches its highest value, which is around minus 15 micromole per square meter per second. And this is during nighttime. This is in the evening. And during the evening, the respiration is actually not very high. The highest value is only about 5 micromole per square meter per second. if we look at the relationship between net radiation and the sensible heat and the latent heat, you can see that for the left panel, this is the sensible heat flux. And you can see the coefficient. This is about 0.09. So it's about zero point 0.1, which is about 10%. So this means only 10% of the net radiation energy is distributed to sensible heat flux. However, for water vapor flux or latent heat fluxes, you can see that the coefficient is 0.25, around 0.25. It means 25% of the net radiation energy is distributed for water vapor flux or evapotranspiration for this rice paddy. So results. During crop season, we find that the maximum CO2 uptake was about 22 micromole per square meter per second. So if we convert this unit into hectare per hour, it means that in Taiwan, in this rice paddy, per hectare, this rice paddy can uptake about 35 kilograms of carbon dioxide per hectare per hour. And in the fallow period, the maximum CO2 emission rate from the soil water surface by the soil respiration was about 5 micromole per square meter per second. So this is about 8 kilograms of carbon dioxide per hectare per hour. However, so then here we are happy with the AD covariance method that they can provide us for measuring and quantifying the net ecosystem exchange. However, this system, the AD covariance system, is so expensive, so we need other things to quantify the net ecosystem exchange or carbon dioxide flux from the ecosystem for Earth. And that's why we need machine learning or modeling. We also used machine learning technique to monitoring carbon dioxide flux for 3 different ecosystems: the grassland in Ireland, rice paddy in Taiwan, and the forest in Taiwan too. Here we use 5 machine learning algorithms, and we have the random forest, multi-layer perceptron. SVM means support vector machine. And the DNN means deep neural neural network. And LSTM is the long short-term memory. So you can see from our results, all these 5 machine learning algorithms produce similar results. So if you are doing machine learning technique for quantifying carbon dioxide flux, then you only need to choose one. Then because the others will produce you the same results. Here I also show you some another greenhouse gas measurement that we did in Ireland in above a grassland, and this is in this experiment we measure the nitrous oxide N2O flux from this grassland because this grassland is a fertilized grassland, and these grasses are actually used for feeding cows. So this is our AD flux tower above the grassland. And this is the results for nitrous oxide flux, N2O flux. And the x-axis is the day of the year. So here I'm showing you the whole year data from January 1st to December 31st. And the y-axis is the quantity of N2O flux. Here you can see N2O flux actually were quite small for most of the time during the year. you can see only some big events for the whole year. Maybe let's see, let's count. This is one event. This is one event. So 1, 2, 3, 4, 5, 6, 7. No, only 7 events. This is because that N2O flux is driven by rain event and the fertilizer application. If you do not apply fertilizer, nitrogen fertilizer into the soil, then the N2O flux will be very small. So you can see that when there's a fertilizer application, there's a big event for N2O flux. See this, or a little bit later that uh, after you apply the fertilizer, maybe a few days later, you will see the N2O flux or N2O emitted from the surface. And also, if there is a big rainfall, you can see some of the event uh, is corresponding to this rainfall event. This is because N2O is produced and uh, by mechanisms of rainfall event. So this is very different. The N2O flux is very different from our carbon dioxide flux. You can see from here, our carbon dioxide flux is a diurnal cycle and it's happening every day. But for N2O flux, it's not happening every day. It's only corresponding to rain event and the fertilizer application. Now let's talk about how do we install and calculate the AD flux data. So for installation of the AD conference system, it's actually that needs some training. And if you do not have such background, then you can actually contact the companies to install the AD conference system for you. And there are two major companies. They are both USA companies, one Lycol, and the other one is Campbell Scientific. And I believe they have the local companies in your country, in Southeast Asia or in your countries too. So then it means that if you have money, then you can buy the AD conference system and the companies can install the AD conference system for you. Now, let's move to data calculation. So you need to calculate the covariance between W prime and C prime bar for the whole day. And actually, we are measuring these greenhouse gases emissions for the whole year. So this is a lot of data. And actually, this is also part of the so-called big data. And for you to calculate these covariance data may be a headache. So for example, for myself, I write my own code to do this calculation. But if you don't have the background of writing codes, then you can use the commercial software. And the most popular commercial software is the so-called AD Pro. So then actually AD Pro is free. So then if you buy the AD conference system from the companies, they will allow you to use the AD Pro software. So then you can do the calculation. Then finally, you need to have the knowledge to do the interpretation of this data. And for the data interpretation, you also need to know another knowledge about this is the so-called flux footprint. And notice that this flux footprint is different from the carbon footprint. So you will notice that this after this. So we know that you hire the company to install the AD conference system for you, and then you have the AD Pro software to calculate the fluxes for you. Then you have to do the estimating for the flux footprint in order to interpret the data that you collected. So now we have to define the flux footprint. Flux footprint is an upwind area where the atmosphere flux measured by an instrument is generated. So for example, your eddy flux tower is here, then the flux footprint can tell you which area is your eddy flux system seeing. So it's tell you how big is the flux, how big is the upwind area that your flux system is seeing. Models are based on dispersion simulation. So actually, we release many particles into the atmosphere and see how these particles are sensed by your eddy covariance system. And then we can know that your eddy covariance system is seeing which area from the end, from the land. So this is the result from the model simulation. You can see this is the areas, and there are three different color lines denoted by different three models. And so, of course, these areas, the areas that your eddy covariance system is seeing depends on the wind direction. Right, because if your wind is from here, then of course you are seeing these areas. If your wind is from here, you are seeing these areas. And these two figures denotes the area that your eddy covariance system is seeing during daytime and the nighttime. And you can see that different models will give you different results. Yes, that's correct. But they are giving you actually not very different, but similar results, especially for these blue line and the white lines. They are quite similar. But for the red line, it's quite different. But it doesn't matter at all, because our major we don't need the exact number, we just need the order of the numbers. So there are actually three major flux footprint models all over the world, and in these models are included in the AD Pro system. So if and this AD Pro commercial software is actually combined with remote sensing data. So that's why if you can give the software your location of your AD covariance tower, you will actually get the map data from the Google Earth. So now let's back to our models. So there are three models, major model, flux footprint models in the AD Pro commercial software. So this is Gadjah in 2024, and Coleman and Maxima in 21, and the Hsieh in 2000. So the flux footprint describes the relative contribution of each upwind service source per unit source strength per unit element to the measured flux. So once again, this flux footprint describes the relative contribution of each upwind service source per unit source strength per unit element to the measured flux. So this is the flux footprint model looks like. And so then you have to give some inputs, and then the model will give you the flux. So the inputs for your measurement height and your surface roughness. And normally surface roughness is 10% of your canopy height and your atmospheric stability parameter. So if you put all these three inputs into the model, this is the result that the model will give you. So these are the results for three different conditions. The stable condition, unstable condition, and the neutral condition. And the x-axis is the distance, and which is the area that your sensor is seeing. And you are placing your sensor at location of 0. And so this is the distance. And this is the relative contribution. So for example, during an unstable condition, your sensor at the 0 location will see a big contribution from this distance. Okay, so it's about like 20 meters away from your eddy convergence tower. And this is the total area that your eddy convergence system will see. So this the total distance is the and it is termed as fetch. And but there's a general rule for you to understand this if you don't want to use the model. This rule is the height to fetch ratio. It's 1 to 100. It means if your measurement height is 1 meter above the ground, the fetch or the area that your eddy convergence system will see is 100 meter. So then, of course, if you set up your eddy convergence system at a higher height, for example, at 5 meters, but you cannot, but you cannot put your eddy convergence system under the canopy height. Or for this, because this is one-dimensional flux footprint model, then we can expand this one-dimensional flux footprint model into two-dimensional. It means that you can see an area in the not only in the x direction but also in the y direction. And I'm not going to too detail about this y direction, but you can see that the map you an area. So it's like this results. So if you put the wind direction, if you put the wind direction into your simulation, then you will get some results like this. And this is for stable condition. This is for unstable condition. And the dot means that the distance that your sensor is seeing. For unstable conditions, you can see that you can see that for this site, there is a major wind direction, from the 120 degree and to the 300 degree. And then under unstable condition, most of the data, most of the data is from area within 500 meters. And the longest is about 1,000 meters. But for stable condition, the area is quite big. It's about 5,000 meters. And the longest may be up to 10,000 meters. In stable condition, it means during nighttime. Now let's move to the third part, microclimate practical interventions. So here I will talk about several intervention techniques. And the first one is the agricultural resistance to cold weather, the frost farm. And then the second part is about building energy saving and increasing thermal comfort by wind tower, water spray system, green roof, cool roof, and the solar farm. So when air temperature is low, the tea leaves may be damaged by frost like this. So the tea farmers, that they use this frost fan to prevent the tea leaves to be damaged by frost. So normally, these big fans are very big. It's about 5 to 6.5 meters tall. And the distance between two fans is about 20 to 30 meters. And when these fans are turned on, the advection wind speed is about 1 meter per second. And when to turn on this frost fan is when the air temperature is dropped to 3 to 5 degrees Celsius. And then you start using this frost fan to prevent a low temperature in the tea leaves. So this is the whole idea. During nighttime, when the temperature is low in the surface and the temperature is high in the atmosphere, so you turn on the fan to create turbulence, and then create sensible heat flux downward. And then so this downward sensible heat flux will warm up the tea leaves. So then the tea leaves temperature will be higher than 0 degree. So then this in this situation, the tea leaves will not be damaged by the 0 degree temperature. Now let's talk about other technique. Building energy saving by micrometeorology management, wind tower, water spray system, green roof, cool roof, and the solar panel. So for the wind tower, this is a technique normally used in Middle East. So this is the look of the wind tower. And these photos are taken by myself when I visited Dubai, and this is actually in a museum. So this is the whole idea of a wind tower and the house in actually this is in Iran. So the wind tower can capture the wind at a higher height. And the wind at a higher height during the daytime is cooler than the air temperature is cooler than the temperature near the surface, because during daytime the temperature is higher at a higher height, and the temperature no, sorry, the temperature is lower at a higher height and lower near the surface. So if we can catch up the lower temperature wind at the higher height, and then direct this wind, this low temperature wind into a house, then this can cool our house. And after this low temperature wind is warmed up by the indoor air, then the warmer temperature is released into the atmosphere from the other outlet of the wind tower. So this is the whole idea of the wind tower. And this technique is now actually still used in yachts in Iran. And another technique is the water spray systems. And this water spray system is quite popular in the Southeast Asia. So if we have a urban Kenya, then these actually are our water spray system. So in our simulation, we have 7 water spray systems in our Kenya on both sides. Then we monitor the impacts of this water spray system in our air temperature within the urban Kenya. So this is a photo taken by myself in Chiang-I in Thailand this year, 2026, when I visited Chiang-I University this year in January. And this is the result. So the H over W ratio is the height to width ratio. Height is urban canopy height. Width is the street width. So if H over W is small, it means that your urban canyon is wider. If H over W is bigger, then it means your urban canyon is narrow. RH is relative humidity. So we have different cases when the relative humidity is 70% and when the relative humidity is 80%. The x-axis is the space of is the width of your urban canyon. The y-axis is the height of your urban canyon. You can see that if your urban canyon is narrow and the different colors means different temperature. The darker that means the temperature is higher. The lighter that means the temperature is lower. And these two circles denotes our water spread system along the urban canyon. And you can see when the urban canyon is narrow, then this water spread system's efficiency is higher because you can see that the area in the urban canyon is bigger. The lower air temperature area is bigger than in the wider urban canyon. And however, if the relative humidity is increased from 70% to 80%, you can see that the temperature reduction is not quite good compared to the 70%. So it means that this water spread system's efficiency depends on the relative humidity. If the atmosphere is drier, then this water spread system efficiency is better. If the relative humidity is higher in your local environment, then it means this water spread system is not very useful for reducing air temperature in the outside environment. So results, the simulations showed that the most effective cooling area was the area just under the spray nozzles. However, in a narrow street canyon, people in the middle of the street may feel the cooling effect because of the dispersion and the accumulation of the cooled air. Our simulations revealed that under drier conditions, the water spread systems will have higher cooling performance. We also found that using large water droplets created a wider cooling area in the middle of the street canyon. Now let's talk about green roof. This is the green roof experiment that we have done in National Taiwan University. So you can see we have different green roof types. And also known as a reflective roof. So a cool roof is a reflective roof and is a roof with high solar reflectivity and high thermal emissivity. So then they can reflect the solar radiation and keep the buildings cooler than normal. And constructing a cool roof simply involves applying a high reflectivity coating to the roof surface, commonly referred to as heat insulating paint. So this is an example. This is the cool roof in National Taiwan University. So we applied white heat insulation paint to the whole roof. And here you can see our metrology station on the rooftop. And this is when I'm showing the students. And this cool roof is not only a cool roof, but also a rainwater harvesting system. So this is before we construct the cool roof. This is after we construct the cool roof. You can see the difference. So this is showing that the channel that are collecting rainfall and then stored the rainfall on the ground. So this is the channel correction for raining water. So these are the pipes to collect the rainwater from the roof. And this is the storage for collecting for storage of the rainwater. And the annual water collected during the whole year for this site. And so in Taiwan, normally our annual precipitation is 2,500 millimeter, and our area is 1,500 square meters. So the total is about 3,700 tons of water. So results. A simulation study by Yang indicated that both cool roofs and green roofs can reduce energy demand by decreasing heat flux. The study found that during peak summer hours in Singapore, 9 a.m. to 5 p.m., cool roofs reduced heat absorption by approximately 0.14 kilowatt hour per square meter, while green roofs had a significantly lower effect at approximately 0.008 kilowatt hour per square meter. So this is the results by Yang. They are saying that cool roof efficiency is better than the green roofs. Bended found that in Melbourne, the heating cost of cool roofs overweighted their cooling benefits compared to dark roofs. In the tropical climate at Darwin, applying cool roofs reduced total cooling and heating loads by up to 14%. So these results are telling us that cool roofs are good for tropical weather, but are not very good for temperate weather like in Melbourne. But so this means cool roof can be applied efficiently for Southeast Asia climate. However, we still need to think about construction and maintenance costs for green roofs and cool roofs. Another way to keep the building cooler is to put the solar panels on the rooftop to prevent the roof absorbing solar radiation from the sun. And so now we are studying the impacts of local temperature and the rainfall by solar panels. So we did a model simulation for Taipei City, so that actually we replaced all the roofs, not most of, all the roofs, building roofs in Taipei City by solar panel, and see how this solar panel will influence the local temperature and the rainfall. So our model simulation is carried out by mesoscale weather model, the so-called WRF model, the weather research and the forecasting model. And we also have a land surface model, LSM, and urban canopy model, UCM. So we combined WRF, WRF model, LSM, and the urban canopy model to get the results. We have two scenarios. The first scenario is that the solar panel albedo is 0.12. And another scenario is that in a future scenario, when the solar panel efficiency is 30%. And now the solar panel efficiency is only 17%, but we believe in the future that this efficiency can be increased to 30%. So we called these two scenarios EF17 and EF30. So under the current solar panel efficiency, this is the EF 17 percent case, and different colors means different temperature reduction. So we can find out that under 17%, if in Taipei City, this area is Taipei. In Taipei, if all the building roofs are replaced by solar panel, and the solar panel efficiency is 17%, we can see that the air temperature will be released by about 0.5 degree or about 1 degree. And by 30%, this is about like 0.75 degree or 1 degree. And this is the change by rainfall. And actually, the rainfall is reduced by by about 10 millimeters. And if in the future the efficiency is higher, then the temperature is dropped more, about like 15 millimeters. So in conclusion, our simulations showed that installing solar panels in the rooftop in Taipei City will reduce temperatures and afternoon thunderstorms. However, we noticed that another study in the United Arab Emirates has different results from our results. So the title of this study is Scaling Artificial Heat Islands to Enhance Precipitation in the United Arab Emirates. Solar farms in the United Arab Emirates are approaching the size where they might create their own weather. So if these solar panel size or solar farm size are big, then they can create their own weather. So their study shows that if this solar panel is a 10 kilometer square, then it had very little impact. However, if your solar panel is bigger, has the size of 20 kilometer square, so it means uh, uh, for both sides, you have 20 kilometer, for this square is 20 kilometer times 20 kilometer. And from this 20 kilometer square upwards, there is a strong scale dependence, with solar panel size influencing the strength of convective process and the volume of rainfall. In terms of rainfall increases, 20 kilometer square produces a mean rainfall increase over the control simulation of about 600,000 cubic meter per day, with the other sizes as follows: 30 kilometer about 1 million cubic meter per day, 40 kilometer square about 1.5 million, and 50 kilometer square about 2.3 million per cubic meter per day. So this study tells us that if you have a big enough solar panel farm, it can actually create rainfall for this site. And this site is in the United Arab Emirates, where they need water a lot. And some large expanses of dark solar panels can cause updrafts that, in the right conditions, lead to rainstorms, providing water for tens of thousands of people. But in our study in Taipei, the solar panel will reduce the local temperature, but will reduce the local temperature and reduce the rainfall. But this study, they said this will create rainfall for United Arab Emirates. So the solar panel impacts are actually are actually dependent on your location. So CO2 reduction by solar farm, now that we need to do a calculation. So with a carbon emission coefficient of about 0.5 kilogram per degree in Taiwan. One solar panel generates about 460 kilowatt per hour of electricity per year. And then times this coefficient 0.5 equals to a reduction of about 230 kilograms of carbon dioxide per year. So this is the one solar panel will create a reduction of 234 kilograms of carbon dioxide per year. But how big is the one solar panel? It's about 1.8 square meters. Let's take about 2 square meters because when you are installing the solar panel, you need some extra space. So 1 square meter of solar panel will reduce about 100 kilogram of carbon dioxide per year. This is much bigger than the forest. So should we use solar panel and to create electricity for us if we have a land? And then we can generate the so-called green power, and then have the ability to combat the climate change. But then we have to think about environmental impacts of these solar panel farms, and this is the Taiwan case.
I'm sorry, Professor, your time is
Yes.
5 minutes left.
Okay. All right. Okay, I will try to finish this in 5 minutes.
Okay.
So the installation type of solar panel, and this solar panel is the so-called photovoltaic. And we have 3 types: rooftop, ground-based, and floating. So the rooftop is the solar panel can be installed in the residential area, commercial area like this. But the environmental impact is the glare. You can see the glare here is very obvious. So if your neighbors, well, if I'm your neighbor, I will be complaining about this. How about the ground-based system? So in Taiwan, they use agricultural forest pond to install this ground-based system. So this is the case in Taiwan. They cut off the trees, they remove the agricultural land to install these solar panels. So then we have the environmental impacts about landscape change, future aesthetics, local climate, ecosystem change, and even food shortage because you are replacing agricultural land with the solar panel farm. And they even put this solar panel farm in fish breeding pond. So you can see this is fish breeding pond, and they install the solar panel. And after they install the solar panel, you cannot have any fishes here anymore. And the floating system. So this is the floating system. So the environmental impact is landscape change, future aesthetic, and the local climate. So overall, the environmental impacts of solar farm that you need to consider is exposure to hazardous chemicals like PM 2.5, SOx, NOx, mercury, noise, water usage, light pollution, glare, recreational resources, future aesthetic, climate change, local temperature, global temperature, and air temperature increased or decreased, and also rainfall, and land occupation, habitat, ecosystem, food shortage. So in conclusions, microclimate practical interventions like frost fan, wind tower, water spray system, green roof, cool roof, solar panel are found to be energy saving and effective for improving the comfort of living. However, when building solar farms to provide electricity, great care should be taken into account their environmental impact. And for a small country in Taiwan, our country land area is very small. So then we have to think about this more carefully, even more seriously than countries with bigger areas. That's all my lectures. Thank you very much.
Okay, thank you so much, Professor. And just briefly, we today already study about the carbon farming, and it's not just a concept, right? So we know how it's practical and how they can be like pathway to climate mitigation, and we also we know that accurate environment measurement, like Professor already told us like about the eddy covariance method and anything that I think is very knowledge that new for us. And I saw we also know the some implementation of that like solar system and everything that I think is very good presentation. Thank you so much, Professor Hsieh.
Yeah,
And
thank you.
before we close, I have like some time for Q&A session. Maybe there is someone that want to talk or want to asking something to Professor. I think it's very great opportunity to asking directly
Yeah.
to Professor. I give like
Yes.
a three question. Okay. Is Sam, you can yes.
Okay. So sharing the data, sharing the slides.
Yes.
Okay. All right.
Okay.
Okay. Thank you very much.
Hello, Dr. Chen. I
Yes.
thank you for your extensive research in micromanagement of carbon sequestration. And uh, I have a question about the eddy covariance instrument. So you you mentioned earlier that this instrument is expensive and it needs improvement for uh, what do you call this? Okay, so I will get to the question. So based on how you use the eddy covariance system, how will you improve or make the system more efficient in carbon detection? And what limitations did you face that could be improved by future researchers?
Okay. Thank you very much for your question. Uh, so these eddy covariance system actually now are used by two ways. One way is for research, for scientific purposes. So like what we are doing. And another way is to quantify your, you know, carbon releasing by your country. So if your country have a forest, and you can, claim for carbon credit, and then this can be taken into account for your total carbon dioxide releasing from your country. And this is part of the Paris Agreement. So for you to quantify your carbon credit from your forest or other ecosystems like peatland or wetland or other ecosystems, then you need a scientific data. So that's why these AD covariance systems are used to quantify the carbon credit from every of these ecosystems, and they are believed to be the best methods for now to quantify these carbon credits. But these are expensive, and actually they have many limitations. For example, we assume steady state and horizontal homogeneity, and then so this means that your site should be a flat site, no uphill, no downhill. So, but normally it's our forest is in the mountain, right? So in the mountain that to install eddy covariance system, it needs to do some adjustment and corrections. So that's how these eddy covariance systems still need some corrections. And then this is how we can improve the precision of this method. And there are other assumptions that we also need to take into account. For example, the steady state assumptions. So these are the methods that you need you improve. Although eddy covariance system is thought to be now the most accurate, but it still has some spaces to be improved. And then these are expensive. So these are expensive. So like for example, one eddy conversion system will cost about 1 million Taiwan dollars, which is about 1 million Taiwan too. And this is about like 30,000 USD. So, but you you need many of these systems. So, but if you so that's why we need the modeling. So most of the time you can install these systems in one of your ecosystems and use machine learning model or other models to predict the carbon credit or carbon dioxide uptake. Then later on, you can move these systems, this adequate system to another ecosystem, and then train your machine learning model. Then to have a machine learning model which is good for this ecosystem to predict your carbon credit for the future climate. Then so you can have your machine learning model for each different ecosystems. And then so you don't need to spend too much money on buying a lot of AD conversion systems to quantify, your carbon, AD conversion system, your ecosystems for carbon credit. But for now, all over the world, there's a net called FluxNet, which are providing flux data all over the world. And I believe there are already like probably more than 700 flux tower sites that can provide you data, active flux data for different ecosystems. Okay, I hope I answer all your questions.
Yes, Dr. Chen, thank you. And realized that there's a lot of brainstorming ideas needed to improve this tech. Thank you, Dr. Chen.
Thank you.
Okay, anyone have another question? Okay, let's.
Hello, good morning, Professor Cheng. I'm
Yeah.
Dom from the Philippines. I was fascinated with the last part of your presentation on solar panels. And this is just a hunch because nowadays we know that the solar panels are very popular because of its advantages. But in your own point of view, may I ask if later on, if in a large scale usage of solar panels, there be a challenge on disposal in the future, especially if we will not it's the if the use of the solar panels will end out of its function. Thank you.
It's for constructing solar panel and the solar farms for providing electricity, you need land. You need a large area of land. So, and this land should not be, forest, wetland, peatlands. Although you are not using these lands, but forests have the function, of like for various animals. They have their the so-called ecosystem function. Not only uh, providing an uptake for carbon dioxide, and they also provide habitats to a lot of animals. They also regulate the local climate, right? So, if you are installing, solar panels, then you should use those lands that are not currently used. And they cannot be a forest or a peatland or a grassland. It should be some spare spaces that you are not using it at all, like a desert. So, like for example, like in Taiwan, now we are actually installing solar farm in a reservoir. And I don't think this is a good idea, but they are already doing this because I think you do want a reservoir, that you can enjoy the view, but not a reservoir that you are seeing a solar panel. So especially for for you have a limited area space area. So and as what I was talking about, that there are results, simulation results showing that when these solar panels are big enough, they will actually influence they will actually influence the local temperature, local weather, and even change the precipitation on your local area. So you got to be very careful about installing these large solar farms. And when they are too large, they create another microclimate, and you have to be careful. And from my point of view, I think rooftop solar panel is now the best way to do this because if you are not using your rooftop for green roof, cool roof, and then if you install solar panel on your roof, they can create insulation for preventing your building to absorb too much solar energy, and then create electricity for your building. And then also the environmental impact of this rooftop solar panel is not that big. You only have to care about the glare, the influence to your neighbor. So, but if you are not in area that this light pollution is serious, then I think rooftop solar panel is the best thing that we can do. Okay.
Thank you very much.
Okay, and I encourage the online participant. You can like ask from the chat box or from the you can like on mic and call in person. But I saw one from Nurhayati Tarigan. They have one question, Professor. Could you
Yes.
please tell us how solar panel can affect rainfall and what mechanism drive this phenomena?
Okay. Why the solar panel can influence the rainfall. It's because first of all, this solar panel should be in a big size. In a big size. There are two simulations in my lecture. One simulation is in Taipei City. So, but this is very big. We replace all the building roofs in Taipei with solar panel. So it's a big size. And the other study is in the United Arab Emirates. Their size is 20 kilometer by 20 kilometer. If it's only 10 kilometer by 10 kilometer, the influence is very little. So this is the first thing, that your solar panels should be in a very big size. And the second thing is when you put solar panel, these solar panels reflect. They absorb most of the solar energy because they want to use this solar energy to generate electricity. So the reflectivity of each solar panel is low. It's only 0.12. It's very, very low. So most of the solar energy is absorbed and to generate electricity. But the solar panel will be hot, and they can heating the air temperature around your solar panel, and then create an upward air move. So then this updraft of air move will create another advection. So this will change the mixing layer of the boundary layer. The mixing of the boundary layer, then create another uh, weather type. So that's why this solar panel is influencing the precipitation. It's by they are creating another boundary layer phenomena, and it's also important why the rainfall is changed. It's because of the moisture. If you are only influencing the air move, it's not enough. You still need humidity. So this is only under some cases that there are enough humidity or there are not enough humidity. So in the simulation case in the United Arab Emirates, there's only under the case that when there is a moist air from the sea to the United Arab Emirates, then the precipitation will be increased by installing a big size of solar farm. So I hope this answers your question.
Okay, thank you very much. And I think one last question for the floor and from the online participant. There is another question, maybe from the online. Uh, okay, I think I have one question, Professor. So the thing is very insightful for me, especially I'm not work with the solar panel, but I think I work with environmental friendly. So what the biggest barrier to implementing the carbon farming globally? Like what the biggest like limitation or something that we cannot like do it for globally?
Actually, for carbon farming, for the 4 per thousand initiative, actually their goal is to do it globally. Yeah, they hope all the farmers in all over the world, can increase the soil organic carbon by 0.4%. But actually, this is difficult. As I was talking about that, when the soil organic carbon is increased in the soil, then the respiration rate will be increased too. So when uh, when you are in one direction, you are doing carbon farming uh, to get CO2 in from the atmosphere into the soil by your plant photosynthesis. Then in the other direction, that the soil respiration reaction will generate carbon dioxide from the soil to your atmosphere. And so you need to do more study about this to see how this can be balanced. But more difficult thing is that how do we put your crop, roots, stalks, leaves into the soil. So you need to sometimes the farmers burn the leaves and then to get fertilizers. And then when the leaves are burned, they are ashes. These ashes can be easily, merged into the soil, and this is carbon farming too. But when you burn it, there's not much carbon, stored in the ashes. Most of them are, released back into the soil, only small part. And then you also need a machine to grind the leaves or the roots or the stalks into the soil. So then you later on you may reach the maximum capacity. So it's not that kind of easy. And when you are using machine, you need oil, and then you are generating another CO2 releasing into the atmosphere. So that's why you need to think about this. And in Taiwan, actually, we have some farmers that actually they are doing this. they are trying to follow the 4 per thousand initiative and to grow their crops. And then one thing that I learned from their result is that once the soil organic carbon is increased in the soil, they said that the crop uh, productivity is better than before. This is what they say. Okay, thank you.
Okay, thank you. I think I have another question from the online participant. So, just a curiosity of mine is that is it possible to create a collapsible, foldable, retractable solar panel in the future? Just this modification could affect to the efficiency, like electricity source, something like that.
Well, sorry, can you repeat the question again? I
Yeah.
didn't get the point.
Just a curiosity of mine, is that possible to create like collapsible, foldable, and retractable solar panel in the future? Does this modification could affect to the efficiency, like the electricity source?
Oh, okay, okay. Well, this is actually a good question. Uh, yes, of course. When the solar panel is exposed to the air, and then air pollution will cause some problems. PM, the dry deposition or dust will be on the solar panel, so then the efficiency of the solar panel will be reduced. That's why they have to clean it up, frequently. But they do cleaning up the solar panel, not frequently using just use water. And then also this problem can be applied to cool roofs. Cool roofs has the aging problem. Cool roofs reflectivity efficiency will be also influenced by dust. So that's why when you are using cool roof uh, to reduce to reduce heat from the sun for the building. That this is one of the questions that you have to take into account. Okay, thank you very much for this question. Do I answer all the questions?
Yes, you already answered all. So I think thank you so much for Professor Hsieh and another participant for today. So for the closing, this session has shown the understanding of microclimate process, and it's not the scientific perspective, but we also highly practical for like building the climate resilience. And I would like to express our serious appreciation to our speaker, Professor Cheng-I, for the valuable insights shared today. And thank you so much for your attention, and thank you so much for Professor Hsieh or
Yeah.
for sharing
Thank
with
you very
us
much.
today.
Yeah. Thank
Thank
you.
you.
Bye.
Okay, thank you so much to Professor Cheng-I for being insightful lecturer about climate resilience through microclimate management, from field condition to practical intervention. We would like to give the appreciation certificate that will be given, symbolized by our moderator.
Thank you.
Okay.
May we give a round of applause for the speakers. Thank you, Prof. Chang.
Thank you very much.
And also we would like to thank Mr. Nafis Diskulo Azimi, who led the discussion before, and the certificate of appreciation will be given by the chairman of the Short Course 2026 program, Dr. Rizky Maftuka. Okay, now will be given by Dr. Hilda. Let me give a round of applause for the moderator. Thank you. With the session of appreciation certificate already implemented, then the first material of this short course has ended. For operators, you may stop the recording for the first session. Thank you. And for the announcement, for all, we also remind you to